promised you last time, I hope I keep that promise, that this will be better than some of the heavy G algebra that you had to do, especially in spherical coordinates and change of variable, right? They were pretty heavy G. So I'm going to introduce you, what for most of you is a unique thing that you've probably never seen before. And that's a vector field, also called a vector function. And this is what they look like. We'll take a step back and we'll come and do that. That is a good old-fashioned function. Technically, it's two-dimensional, isn't it? You know, if you sketch it, it would look something like that, right? Yeah, it's two-dimensional because, right, if you want to draw the points, you get a curve, right? Now, if you move up to functions that we have been dealing with, like a guy like that, sometimes also written in that format, they're totally equivalent. Isn't that a 3D situation? Hey, trust me, it looks like an acorn, right? But it goes on forever. But the properties of these kinds of functions is that no matter how many variables you put in, there's a single number that pops out, right? You might put in two variables, but don't you only get a single answer? Oh, shooting space. They told me they weren't coming today to do the roof because it was raining. So either part of my roof has just fallen down or they've arrived. Okay, so keep going. Here is the new guy in town. A vector field, also called a vector function, has a totally different answer. You do not get a single scalar out. You get a vector out. So you plug in an X and a Y and a vector comes out. You plug in an X and Y coordinate and a vector comes out. Now, if you try and think, what on earth does that look like? It's not really a 2D thing anymore. It's not even a 3D thing anymore. Those terms really don't help. What you can imagine is that at every single point in 2D space, right, every X and Y that you could possibly pick, the answer is going to be a vector. So for instance, if I choose the point 1, 1, right, 1, 1. At the point 1, 1, what I will get is the vector 2, 0. Now the vector 2, 0 would basically be that vector there, right? Now if I picked a point like 2, 1, which would be here, then I'd get 2 add 1 is 3, 2 take 1, I'd get a 3, 1, I'd get a vector that looks like that. In fact, if you took every single point in the universe here, won't your answer just be full of lots of vectors? So a vector field or a vector function takes a two-dimensional point and returns a 2D diagram where every point, every single point, even the ones like 1.1, 2.1, is a vector. Now, what on earth are they used for? Those are needed because if you want to model, oh, I know, current in a river. Can you imagine a current in a river? Couldn't this be modeling it? Can you imagine if the vectors did this? Making this up. But can you imagine if the vectors do that? Don't you get a feeling that the current's going this way and then it's kind of branching outwards? You see it? It's coming like this and then it's kind of branching outwards. Can you imagine people trying to model wind in a 3D atmosphere, right? At any given point on a hurricane, aren't some of the winds blowing this way and some of the wind is blowing in a totally different way? Aren't those all vectors? I'm blowing that way and the length of me is how strong I'm blowing. So if you want to model magnetic fields, flux, wind, magnetism, whatever, heat flow, you need this kind of math to do it. Would you agree? None of the math that we had up to this point allowed us to model a kind of situation like this, right? Now, a lot of the questions you're going to be given ask you to draw them. And if you had to do them by hand, you'd be here all day. So let's show you that there's a lovely piece of software that does that for us. And I'm just checking it out now. Here we go. Are you looking at a thing called vector fields? Right. Now, if you go here, right, and you look at your vector field, I'm hoping this thing doesn't crash on me. Right. If I change this to x add y, I don't know why they called it that, but basically x add y is the guy that goes there. And if you change this one to x minus y, you'll actually see what this vector field looks like if I click off it. There. Now, if you find these arrows are a little bit small, I believe you can adjust them with this and with this. There. Now that looks pretty good. Can you see the model of what this is looking like? I like to think of this as river currents as the wind blowing. Can you see this vector field? It swirls up this way, swirls down that way. On this way, isn't it kind of got a branch where sometimes it curves to the left and the ones that curve to the right go like this? And then what's it down here? It kind of curves up and then it curves up. There's a kind of dead space in the middle. Would you agree that everything seems to be trying to avoid the center? That's what a vector field looks like. Now, I can play about with these and I have no idea what's going to happen when I do this, but it's almost fun. Let's make that x squared. Hopefully it can take an x squared in that format. There's an x squared. I'll click off it and find out. It can take it. Let's make this one a much simpler one. Let's just make this 2 times x. And these vectors are a little bit too big to see. So I think which one? Oh, these ones too big to see. Let's shrink them back. There. Can you see the information that's going on there? Isn't it kind of cool what a vector field can do? It allows you to model something. The length of the vector gives you an idea of force or velocity, right? And obviously the direction that it's pointing. This one also has a kind of weird thing going on, where as you head towards the center, doesn't the wind essentially die away to nothing? Although I wouldn't call this a tornado, because tornado needs a kind of curve to it. Don't tornadoes have a, in the center of them, isn't there a quiet spot? Or can you see that if you were modeling, the quiet spot would be here? And as you travel further away, the winds tend to get more and more violent. Let's try one last one and see if I can make something interesting happen. I hope it can take a cosine, because trig functions generate some really nice, weird shapes. Okay. Can I adjust the size of them? Come on, help me out here. Be nice. Okay, if you're not going to cooperate, then I'm going to put a number on it to try and make it bigger. I think the problem here is that the cosine is so small. Yeah, that should help. There we go. Ah, there, that's nicer. You see? Some really quite interesting swirls and curves going on here. For instance, at this point here, right, this vertical line, do you notice that the wind comes round and then it shoots upwards? Or if this was a river current, wouldn't this be a riptide, right? You don't want to be there, because at that point the currents are coming together and shooting upwards, and evidently on this side it's shooting downwards. Excuse me. Let's go. Show you some questions. It's a very short section, this one. As I said, it's mostly looking at using that software that I just gave you to, where the heck are you? Here we go. There we are. I don't want to do that. Go away, solutions. Go away, solutions. Right. So here is your vector field function, and it's written as -19i and y minus x. That's the ij notation. You know, I like the little brackets. So in my case, this would be -1/9 y minus x. One of these four pictures is the right one, and I'm pretending it's that one. Right, in this one, it's a y and an x plus y. Oh, let's try it. Without the software. Anybody want a predictor on which of these four shapes might be the visual representation of this vector field? Right, here we go. Any suggestions? Well, you could basically just pick some spots, you know, like 0, 0, 0, 1, 1, 0, 0, -1, 0, -1, and get like 4 little snapshots and then go through each one of the 4 that works. For instance, if you make the x and the y equal to each other, won't the j component be 0? And if the j component is 0, doesn't that mean a horizontal line, right? Like 4, 0, 2, 0, 7, 0. So I'm looking at y equals x, which is a line going this way. And anything on this line y equals x, all I should see are horizontals when that happens. Now, I can't see any of those horizontals. So is that my eyesight? Nope, that's not horizontal. That's a dot. That ain't horizontal. And I'm saying it's horizontal in that sense, but obviously I forgot to pay attention to that one. So it means all of them are pointing at -1/9, 0. So pointing that way and horizontal. Yeah, it is horizontal. I can't tell you. I don't know.
Should be number.
But that's should be 1.
Yeah, it should be 1.
Tell me why. I can't. This is so small. At least my eyesight, it's so small. Are these little dots representing the y equals x I'm talking about?
That's what I think it's representing.
Yeah.
But
Well, let's find out. I'm going. I think I should have picked a layer one. That one's a hard. Is it? No, it's that one, which is also a whole load of dots. So they'll look the same. Right. I can't get this one here. I better switch those answers off. But when you put it into that software, you should hopefully see something that looks like the ones you've got. Oh, that one's a pretty one. That's Bailey coming in. He's fed up barking. Any suggestions on? Let's shrink this. Can I? I can't shrink it.
2?
Yeah, 2. Looks interesting. It's actually the 3rd one. Why would it be the 3rd one? Okay, let's look at it. If those 2 guys there, what would they be? Why would it be 2? Well, when you make y equals x, you get straight lines of some sort. So if y equals x, that becomes y squared. That becomes a straight line. I guess that's it. I guess the moral of this story is Thank goodness for the software. Because I bet you if you put it in, it would be one of those. As you can see, aren't most of these questions just, here's a force field, match the answer. Here's a force field, match the answer, right? So far, so good. Now, there are a couple of questions at the end, so let me show you what else you can do with a force field, apart from guessing and getting it wrong, in my case, or putting it into software and getting it right. What you can also do is you can find, or you can create vector fields from normal functions. So this is an example of a normal function that we have dealt with before. I'll just pick a nice easy one. Let's take that one. If I asked you to find this guy, and then I asked you to find that guy, are you comfortable with the notation? Actually, normally you would just write that down, wouldn't you? So we're going to find the partial derivative with respect to x. And if you find the partial derivative with respect to x, get that. And if you find the partial derivative with respect to y, you get that. And then we have a guy which we have met before, and he is now returned. We are going to get what's called the gradient vector field, or as we just called it in the past, the gradient. Remember him? And so in this case, the gradient of the function f would be partial derivative of x, partial derivative of y. So 8y cosine x, 8 sine x. So we've actually met a vector function. We just never told you it was a vector function, or a gradient vector field, as its other name is. But they're quite useful. Are you comfortable about finding the gradient of a function? Pick another one of these guys. Question 8. We're being asked to find the gradient vector. God, they get so many different names for these: the gradient function, the gradient field of that guy. In other words, partial derivative x, partial derivative y, partial derivative of z. Is there anything I can do to make my life simpler in this question?
It's symmetrical.
Right. So whenever I get the answer to this one, shouldn't I be able to predict the other two without having to do them from scratch? Also, for this guy up here, shouldn't we call it a half power? Because if you're going to differentiate it, right, you have to do that. Right. So if I multiply by the power, and then I reduce the power by 1, I get that. And then remember to, because it's technically as a chain rule, to differentiate the inside with respect to x. The final answer I get is 9. Bring this guy downstairs, put an x there, and call it a half, and then make it look like the original. Are you comfortable about the partial derivative of this function with respect to x being that guy? Are we good? Right, now if you want to do the other two, don't you just say 9y over the same square root and 9z over the same square root, and you're good to go. So there are two groups of questions here. One is, here is a function, right? Draw a graph using that software and tell me which one of the 4 pictures does it look like. The second group of questions are, here is a normal function, find a gradient vector for it, which is what we've just done here. And now they kind of put the two together. An example of that is question 9, where they give you a function, which is this guy, and they ask you to find out which of the 4 pictures below is the gradient vector. So first you get the gradient vector, which in this case is 2 lots of x plus y times 1, comma, oh, that's boring, 2 lots of x plus y, right? Would you agree both of these are the same? Just coincidence. And then you plug that into the software and you have 4 guys, right? One of which is the right picture. From what I'm looking at here, won't the x and y be the same guy each time? So I'm looking for vectors that go 1, 1, and I'm looking like -1, -1, right? So all these guys here are going 1, 1, and 2, 2. They just get bigger. But they're all at 40. I know it doesn't look like it, but they're all at 45 degrees. Right. And what about the guys that are here? That's -1, -1, and so on. Well, they all go that way. These guys go this way. I'm pretty sure these guys go this way, and these guys go that way. And according to the ones I'm looking at least, looks like that's the 4th picture. So question 9 gives you a function, create its vector field, put it in the software and find out which picture it is. And question 10 does the same. And we're finished. So it's a very short section. Half the questions, you just plug it into the software and tell me what does it look like. And the rest, you find gradient vectors, and then you put it into the software and looks, see what it looks like. Or you just find a gradient vector and call it good. Now, I do feel I'm skimming through that, but is it okay for me to skim through that? Does it seem there's nothing too messy going on there? Right.
I have a question.
Yes, Dylan. Not Dylan. Yes.
In
David.
the program, how do you get to square root?
Ooh, I haven't tried that, so let me find out. Vector field, I'll switch over and we can all have a little suggestion box if what I do doesn't work, but you would think it should work. So I'm going to go for the most obvious one, which is SQRT. And let's put in an X to see if that works. There you go, SQRT.
Okay.
Interesting. Wonder what happens if I make this square root as well. Only that quadrant should have anything in it then. Ah, there it is. You can play about with these things, although they don't seem to be helping me much. Well, it just makes it zoom in and zoom out. And does that help? Well, it makes them more dots. It's not great. What about that? Oh, that's better. A little bit. If we do a make, there we go. If you play about with the bottom ones, it makes them longer. That way I can see them. So play about with it. If the picture doesn't look clear, you can move these guys around. I mean, you can move any one of these things around and they adjust it in different ways. If we are good, can we move on to the next section now? Okay, I got a lot of nods, so I feel comfortable about moving on. So the next guy in town, our next section at least, is line integrals. So, didn't take them long to get back to integrals, did it? Oh, can you hold on a second? I'm going to have to do some more. We'll never shut them up. Hey, come on. What's up? My apologies. As far as I can tell, something fell off the roof. Well, nothing important, but one of the shovel-y things that they use. I don't know what they're called. Seems to be in the ground. And Bailey was desperate to tell me because it was obviously important in his head. So let's see what a line integral is. Let's do the big picture before we get into the details of how you calculate these things. Okay. I want you to imagine that we have a curve.
Mr. Robertson,
You can't see it?
I can't see what you're writing.
Thank you for telling me. There we go. Imagine that we have a curve, right? Or if a line. I guess a line's, I'd rather call it curve, but it's a line, right? So whatever. This guy. How about thinking of it as a piece of wire, right? And this curve, this piece of wire, it might be given a space curve formula. You remember in Calc 3 that you can describe curves in terms of parametric, yeah, like that guy, okay? And I want you to think of this piece of wire or this thing moving through 3D space, and at any given point on this curve, there is a numerical value attached to it. Let's say it's temperature, right? So can you imagine an aircraft flying through some air, and at different places the air is hot and other places it's cold, and at any given point it's like 40 degrees, 80 degrees, 200 degrees, minus 40 all the way through. What a line integral does, it basically tells you the total amount on the curve. So if you were measuring temperature, the line integral will calculate the total amount of heat energy that that object was picking up or passing through. Can you imagine this is a magnetic field that it's passing through, right? So this is an object passing through a magnetic field. Then the line integral would be telling you the total magnetism that it was passing through, or the total charge if it was coulombs and it was electric field or whatever it might be. And when you write down a line integral, it has a single integral. C is this guy, right? The curve is called C. And you'll have some function. It can be in 2, it can be in 3. Let's say it's in 3 dimensions, right? And you're passing through this curve in your 3-dimensional world or your 2-dimensional world, and then you're going to do your dV. So any given point in 3D space is going to have this value. So you can imagine at that point there, you found the XY coordinate. This here would tell you the temperature at that point. And then you get this one. This would tell you the temperature at that point, and you add them all up. So line integrals are finding total amount of something. as I'm saying up there, on that curve. So if it helps you, that's what you're getting when you do a line integral. So what we have to worry about, or not worry about, what we have to now think about is, how do you calculate a line integral? Because the answer when you're finished will be a number. And it can be positive, it can be negative, it could be zero. Can you imagine a moving object going through an electric field? Couldn't the net effect still be zero? In other words, in some places it was negative, in other places it was positive, but together they balanced. That would be a nice journey if you could do that. So, question 1 asks us to evaluate this line integral. So it's this guy. It's, in this case, it's x over y. They're using ds, that's fine. And we're told what c is. As a parametric curve, it's t cubed, and y is t to the 4. Right? So all we need to do now is use a formula that allows us to take this and turn it into something that we can use. So the generic version is the value of the function ds over some region, and it will now become from t equals a to t equals b. Oh, by the way, this question here, t is going from 1 to 2, right? So that's basically a and b. So integral from t equals a to t equals b. The function, that's this guy, times the square root of dx by dt squared plus dy by dt squared dt. So this is the formula for calculating a line integral of a two-dimensional function going through space. You convert it into a single parametric equation from t equals a to b of the original function, followed by this ugly square root dt. Now let's put all the pieces together. That guy is him, but he gets turned into t cubed over t to the 4, which I make 1 over t. Do you notice that everybody has to turn into t because you're integrating with respect to t? Now, if I find dx by dt, it's 3t squared. If I do dy by dt, it's 4t cubed. If I now put them together inside this square root thing, I will get the square root of that guy squared plus that guy squared. So I will end up with 9t to the 4 plus 16t to the 6. Right, I think I've got all the pieces. So the original line integral is going to be the integral from 1 to 2. The function, the square root bit, dt, and the square root bit ends up being that guy. So far, so good. Right, so I mean, it's a kind of plug and chug formula, isn't it? You just do what the formula says, and you are good to go. We have a bit of a problem here, and it's not a Calc 4 problem, it's really a Calc 2 problem. And it is, how do you integrate things that look like this? And it depends on what you've got, how you're going to approach that. Has anybody got any suggestions about how to deal with this ugly expression? Because right now, it's not going anywhere.
Take out the 2 to the 4 as a t to the 2.
Okay then. So I'll do it a little bit slowly, but what you said is exactly correct. I'm going to pull out t to the 4 as a common factor. I'm going to assume that you would take this out separately. Again, I'm doing this with more lines than you probably would want. And that gets you t squared, but t squared on the top cancels with that guy. So what we are left with is a Mia question. Christian, do you know why I called that a Mia question? Because I'm not going to ask her.
I was hoping you didn't ask me, so.
Oh, no, I'm asking you now. Do you know how you would integrate this?
Mm.
Look at this guy. There's the clue.
Oh, yeah, you would just unsquare root it. It'd be t times.
Oh, no. I'm putting you in the wrong direction there. I'm giving you the wrong clue.
Oh, it's not good.
Keep thinking.
Just take.
Take a U sub.
Oh,
Right.
Okay.
You're trying to make it harder than it is. Whenever I refer to Mia, it's always because it's a U sub. That's why I said it's a Mia question. Is that right, Mia? Poor Mia's gave up. Right. Can you trust me that it is, right? That's a Mia question, right? If it's a U sub, I'm beginning to come to the point where if I don't know what to do, isn't it probably going to end up being a U sub sometime? It just seems to be the theme in this book. Or this. So do that and you're good to go. And that's as far as I want to go with that one. So we have a formula, which I really should probably put it here because I'm going to run short of bits of paper. This fella, and I'm only doing a 2D one, right? So it's integral from a to b of the function square root that guy squared, that guy squared, dt. Okay. If you get a formula in calculus, you should be able to extend it. I don't know what letter of the alphabet they're going to use. I'm just sticking to S. Based on this is what you do when the function is only in terms of x and y. Can you extend it to a curve going through 3D space or 10D space? Well, let's do it through 3D space. It's going to be the integral from a to b, and it's definitely going to finish with dt, and it's definitely going to have x, y, and z going here. Great. What will you do to extend this piece of the formula to now to take care of the fact that there's an x, y, and z? What will this formula here look like now?
Won't it be just the same, the dx by dt squared, dy by dt squared, and then a dz by dt squared?
And it is. And couldn't you keep doing it to 20 dimensions? Not that you'll ever do it, but you could theoretically, right? So if you know it for 2, you know it for 22, don't you? Which is kind of cool. So if you know something, you can extend it to other situations. And that's probably me, again, jumping a little bit ahead of the game. Yeah, we've got time to show you, put that out of the way, to show you another approach to a line integral, because there are 2 versions of what a line integral looks like. That is also a line integral. So I want you to think of C as this guy again. And this fella here has a parametric equation. So let's have this guy being t squared Let's this guy be 3e to the t, right? And let's do t going from, let's say, 0 to 1. Now, in these situations, you really don't have a formula to work by, right? These situations, you have to do things a little bit differently. So show you what's going to happen. Got a little line here. I know that x is equal to t squared, right? They told me that. I also know what dx by dt is. Want it to be 2t. And now the sneaky thing. I now know what the differential dx is. It's that guy. A little line. I know that y is 3e to the t. I know that if you differentiate y with respect to t, you also get 3e to the t. And I know that if I do a little crossover, isn't that kind of one of the things we do when we do change a variable, right? I get that guy. You still with me? Now I'm going to go back to this integral, right? And I'm going to do it from t equals 0 to t equals 1. And x is now going to be replaced by t squared. And dx is going to be replaced by that guy. Plus, x add y is going to be that guy plus that guy times dy, which is going to be replaced by that guy. So essentially, aren't I just substituting everything that has an x and a y and replacing it by the equivalent thing that uses t? Even replacing the dx and the dy in terms of t as well. Now, if you collect like terms together and multiply things out, this guy becomes 2t cubed. This guy becomes 3t squared e to the t, and this guy becomes 9e to the 2t. And isn't there just a single dt now? Would you agree that you can pull out the dt in the way that you could pull out a common factor? Haven't we essentially now got the answer? Don't we just integrate? Now, two of those integrals you can do really easily. So those ones I'll do. Add 1 to the power and divide by the new power. If you want to integrate this guy, you get, well, you do get 9e to the 2t, but what else do you get when you integrate 2d? You get something else. What happens to this guy? Is it times 2 or over 2? What do you do?
You get times
Multiply
one
them.
half.
Right. Oh, there's a third way in it. Times a half. Yeah. I'm not going to do that guy, but I'm going to ask you, can you tell me, and it's not a me one this time, how are you going to integrate that one?
Integration by parts.
Yeah, we finally got an integration by parts. And the only way we got one is because I made that blinking question up. Because the chances are that if you do one of the homework questions, they won't have one. It's almost like integration by parts. No, I think Maggie found one somewhere, right? But they're very rare, right? So integration by parts and off you go. Now, if you look at the two methods side by side, right, would you agree that this method, although it doesn't have a formula, in a lot of ways is easier to deal with than the ugly square root method? If you don't agree, then that's fine. Won't you probably use this method more than that one? And I can imagine certain algebraic situations where one method comes out easier than the other method, right? And vice versa. So you have at least got 2 bullets in your gun now, right? Formula, or, you know, I guess I'll have to give that a name, using differentials, right? To replace everything with t. So far, so good. And we have kind of a good place to finish. So last names and bye-bye, and I will hang about for any questions. Right, so next time, Christian, if I say it's a Mia question, aren't you just going to say, yeah, you sub, you're right?
I'm so tired. I got the dumps. I'm not even gonna lie to you.
Well, I know your brain was suffering from lack of exhaustion.
But I do have a
Really?
question.
Oh, well, that'll make up for it. What you got?
Number 9,
On?
15-9, I think it is.
Okay, so pretty close to the end. Let's have a look at that one.
This has
Number
been killing me.
Number 9. I'll find yours if I can, Christian. Christian. There we go. Number 9. No, it's not near the end. I thought it would be near the end. Okay.
Oh, no, there's more.
So your version of question 9, yeah, I'm on the right one, is a double integral over some region R. Let's kick it onto the white screen so you can see it. So it's a double integral over some region R. The function itself is not too scary. The region R is bounded by the lines y equals 1/2 x and y equals 3 upon 2x. It's also got a hyperbola called xy is a half, and it got another hyperbola where xy is 3/2. And thankfully they told us who x is and who y is, right? So that's at least something, right? So what we're going to do is rewrite this in terms of u and v, right? We're going to do, it doesn't really matter what order we do it in, so I'm just picking this. Here is f of xy. So I'm going to take that and turn it into u's and v's. So it's going to be 7 times u over v times v. The v's cancel, and so that comes out quite nice. Right, so that guy's just 7u. Are we good with that?
Yes.
Next, for no particular reason, let's do the Jacobian piece. So we differentiate with u and then with v. And we do y also with u and then with v. Everybody happy so far?
Yes.
Okay, so forget them, they're a distraction to me. If you differentiate this with respect to u, you get 1 over v. If you differentiate this with respect to v, can you trust me that you get negative u over v squared?
Yeah, that's what I got.
Good. Right, if you do this guy, oh, this guy's easy. If you do him with respect to u, you get 0. And if you do him with respect to v, you get 1. And so major takeaway minor just ends up being 1 over v, which is also quite nice.
Yes.
So the last part, which is typically going to be the hardest, isn't it to find the limits of integration, which means we have to take these fellas and convert them into what do they mean in terms of u and v. So if I start with y equals 1/2 x, if I put in v equals 1/2 u over v, if you cross multiply, you get 2v squared equals u. You comfortable with that?
I think I did v equals the square root of 1/2 u.
Okay, so v squared is 1/2 u. V equals the square root of 1/2 u looks okay to me as well. Now, if I do the next one to it, I can kind of predict that one, isn't it just going to be that fella, right?
Yeah.
So we're good. Let's do xy equals 1/2 now. That's going to be u over v times the, oh, that one is the right way to do it, because don't you just get a number? And you know, one of the pairs has to be a number, right? Either u equals 2 to u equals 7, or v equals 2 to v equals 7, right? One of them has to be numbers, right? Because you're going to have to do a double integral, and the last one must be numbers, or the thing's not going to work. So
Right.
that's good news. If I then put in this fella, I can almost predict the answer anyway. You're going to get 3/2.
Yes.
So we should be setting up an integral using those boundaries and using those boundaries with all the other pieces that come with it. So let's see what they've got. The integral, the double integral of this guy is going to become the integral from u equals 1/2 to u equals 3/2. V is going to be that ugly little guy because he is smaller and this guy is bigger. So I know just by looking at the fractions who's the little guy and who's the big guy.
Yeah.
The 7xy guy became 7u. The Jacobian became 1/v, and the order is do a v, d a u. Are you good up to there?
Yes.
That's great. That's 90% of the work. So you probably just picked up a funny number somewhere or a sign. So let's take our way through and see what goes on next. So in this particular question, I can't separate them, so I'm not going to. This fella with respect to v, right? 7u/v, right? 7u/v. That's going to be 7u natural log of v. You comfortable with 7u/e gets you 7u natural log of v? And then you're going to do it at two very well, I don't know how to describe them. Really ugly looking limits. Okay. So it's going to be u equals 1/2 to u equals 3/2.
Yeah.
And what am I got? I'm going to have 7u, the natural log of the square root of 3/2u.
Yeah. Take
Take away 7u natural log of the ugly square root, that fella,
Yeah.
du. Now, I'm not going to even integrate them until I've done the best I can to make them pretty. So I'm going to do some style points for a couple of lines. I kind of know where I'm going. Square roots are half powers.
Yeah.
Oh, you have a barking dog. That's good. I don't feel so bad.
Yeah, I got 4 dogs.
Oh, you're going to have at least one barking at any given time. Right, are we good so far with the pulling out the half power?
I think that's where I messed up. I just took the
Right.
7u out, and I never put the 2 underneath it.
Right. You could break that apart, but I don't know if it's worth it. So what I would do next is 2 separate questions. They look very similar. They're going to be very similar in value, but the 3/2 and the 1/2 will make a difference, right? They're going to be some numerical. But I would call this guy F, and I'd call this guy G. And guess what? We do get
Integration by parts.
an integration by parts. First time, right? Now, in this particular question, you actually are going to make this the F and that the G, which seems back to front, but you're going to have to do that. And be careful about the 3/2 because, you know, that's part of the answer, right? So if you, for instance, make this your F, then when you differentiate it, you're going to get 1/3/2u times something, times 3/2. Oh God, would you look at that for pretty?
1/u. Yeah.
1/u. Much nicer than I thought it was going to be, right? But, you know, and all the other bits that come. But what is going to happen is that you're just going to have a log, and then I'm not sure if it's going to be plus a u or plus 7u's, but it'll come out pretty nice.
Okay, that's where I messed up. All right, thank you.
I mean, if you're going to mess up at that stage, because the hard bit was the stuff you didn't mess up at, right? Getting the limits integration, you know, doing the Jacobian bit, all that stuff. That's where the brain work lies. Here it's just, you know, tidying things up and getting them to a form that kind of looks pretty.
All right. Well, thank you
Oh, yeah,
again.
not a problem.
Have a good
Maggie, you got one? You too. Bye-bye. You got any, or you can hang about. If you got any questions, Maggie?
Yeah, I do actually. From
Okay.
the same problem set, I really struggled with number 6.
Okay, let me find number 6 in our list. So I've got the same numbers as you. Number 6, where are you? 264. Can I keep these ones for the video? Because
Oh,
they're good
please keep-
questions.
I mine is fine. I don't care about mine, but please keep his because and then I messed up on 9 too. So that was
That was helpful.
pretty helpful. Yeah.
Okay, so where are we off to now? Which one?
Number 6.
Oh, I can see it. Right, it's a gap. You got 7, so 6 must have been whatever. We have a double integral over some region R. It's going to be a 6x and 9y with a dA. Okay, and we're being asked to do a parallelogram, and they give us the coordinates. So it's -2, 4. That goes to 2, -4. Then it goes to 4, -2, and then it finishes at 6, 0. And again, they were nice enough to give us the X and the Y. It's always good when they tell me those. Right, so I look, that should be the same question you were dealing with, right?
Yeah.
Oh, with one exception. 0, 6.
Oh, okay.
Checking the others. Right, I would draw this, well, let's take each piece as it comes. For no particular reason, let's find out what that looks like in terms of U and V. So it's going to be 6 lots of this fella. Add 9 lots of this fella. If I'd thought about it, I would have multiplied those out, but it's too late now. 6 times a third is 2, so you get 2u plus 2v. 9 times a third is 3, so you get 3v, take away 6u. And then when you combine like terms together, you get what? 5v minus 4u. Does that look reasonable?
Yes.
Okay, so we got that guy out of the way. And let's do the Jacobian next. The X with U and the X with V, the Y with U and the Y with V. And if you differentiate this guy with respect to U, you will get a third. And with V, you will get a third. And this guy here, with respect to U, you will get, almost made this mistake there, you'll get -2/3. And with respect to V, you get +1/3. Almost screwed that up, right? -2/3 and 1/3. Do you remember getting things that look like that?
Yes.
So major diagonal is 1/9. Take away -2/9. That gets you 3/9. So the answer is 1/3. Does the Jacobian equal a third look right?
Yes.
So we're good there. Now, the next bit is we need to turn this parallelogram into U's and V's, right? And so the first thing I'm going to do is just plot these points. So 1, 2, -2, 4 is here. 2, -4 is here. Keep these guys in order so we go down that way. Okay. Then we go to 4, -2. Takes me to here. And then we go to 0, 6, which is here. Okay, that looks a bit like a parallelogram. I don't think I screwed up too much. Now, this shape is basically made up of 1, 2, 3, 4 lines, right? And each one of these lines, I'm going to find the equation of them. And they're going to be y equals 2x plus 1, that kind of look. Once I know what that is, I'm going to replace all the x's with this and all the y's with this. And that should generate the limits of integration using u's and v's. Okay, so for instance, let's call this number 1, no particular reason, 3 and 4, right? Line number 1 has a 2 by 2, so its slope is 1, and it passes through 6. So line number 1 is x add 6. Okay, let's do line number 2. What do I know about line number 2? It's 4 going that way, and it's 8 going that way. So it's pointing down the way, and it's got a sloping -2. And it passes through, and you get 6. Third one, from here to here. Well, I know it's parallel to this one, so at least I know it's an x. And I guess I could figure out all sorts of ways of finding out x plus something or x minus something. If I did it in square paper, I could probably just draw the thing and find out where the y-axis is. But since I don't have a very good diagram, I don't want to risk that. So do you see this point here has coordinates 4, -2?
Yes.
If I know that that is on the line, which it is, if I put 4 in here, shouldn't I get -2 out? And so
Yes.
that tells me -6. Does that make sense how I got that guy?
Yeah.
Right. So the fourth and final line, that's this one, is parallel to number 2. So I know that it's -2x. You got to be careful. Just because this went through the origin doesn't mean that it does, right? It might, but let's do a check on it. This point here is 2, -4. And guess what? If you plug in 2, you get -4. It does pass through the origin. We are good. So my picture was pretty good, actually. Now you take each one of them. Let's take line 1 now. And replace the x's with 1/3 u plus v, add 6. And while I'm at it, replace the y with 1/3 v, take away 2u. And let's just see what happens. I get 1/3 u, I get 1/3 v, I get add 6. And over here, I get 1/3 v, take away 2/3 u, is what it is. And if I subtract this from both sides and I subtract this from both sides, what do I get? I get -u equals 6, which means that u equals -6. That's good news, isn't it? We like to see some numbers when we do this. Right, that was line 1. I'm pretty sure that line 3 is probably going to generate something similar. So I'm going to do line 3 next. And it should come out and say u is 10 or u is 5 or 1 or whatever. So line 3 is y equals x take away 6. So it's 1/3 v take away 2/3 u is equal to x, which is 1/3 u plus 1/3 v take away 6, and you get -u equals -6, you get u equals 6, and that is good news as well. So start now with the other 2 lines. Y equals -2 add 6. Y is 1/3 v, take away 2/3 u, negative 2 times x. X is 1/3 u plus 1/3 v. And then I add 6. Right, this one's not going to be a number, but that's okay. And since I already know these are u's, I'm going to rearrange this to be a v equals whatever else. So I'm going to add 2/3 v to both sides. I'm going to add, oh no, would you look at that? I wasn't expecting that. But if you add that to both sides, guess what? I get a v equals 6. I was expecting, you know, v equals 1/2 u plus 3, which would have been fine. Can I tell you what I'm expecting next ones to be? Right?
Right.
Pretty sure. Right. So you put the whole package together now, and we have got the integral from u equals -6 to u equals 6, from v equals -6 to v. It was surprising they got numbers out of that, to be really honest. I was expecting straight lines. Right, that's that bit. We need to know what the function was equal to. And it ended up being what, 5v take away 4u. And then we've put in a Jacobian, which is a third. And then we can do a dv and a du.